So we'll get back to the Coriolis effect a little bit later on. First, let's examine this geometry a little further. The golden spiral is a fractal shape, and we see many other fractal shapes, self-similar shapes throughout nature. Coastlines, trees, lightning, cloud formations, many more. So let's begin by looking into this fractal geometry. We describe the golden spiral numerically using the Fibonacci sequence, the ratio 1.618. But this only describes the fractal shape. It doesn't explain the cause. So fractals occur when a simple rule or an equation is iterated back onto itself many times in a recursive fashion. In this way, a simple rule can manifest as a system of great complexity. Many fractals are so mathematically complex that we needed very fast computers before we could model their fine detail properly. Here is a computer-generated fractal image, and here is a photo that my mom took in the grocery store for me because she knows how I feel about this subject. That's just broccoli. No digital effects are applied. It's an incredible example of natural self-similarity. The most famous fractal is probably the Mandelbrot set, which is based on this quadratic function. And we know how often the quadratic relationship shows up in physics and nature. Anything parabolic, all of the inverse square relationships like gravity and electromagnetism. So let's watch now for a moment as we zoom into the infinite detail and complexity that's generated by a simple quadratic rule iterating onto itself millions of times across many different scale factors. As an aside, by the way, this Mandelbrot equation does use real and imaginary or complex numbers. The complex numbers on the y-axis and the real numbers on the x-axis. Now, some people might think that this means that the shapes that we get out of this kind of math should also be imaginary and shouldn't resemble actual structures in the real world, but this is not the case. Complex numbers are just a mathematical tool that allows us to work more conveniently with rotational motion. It does this because it introduces a recursive oscillating element, because I flips between positive and negative numbers when you rotate its value around a unit circle, like when you use e to the I theta, for example. So I simply transforms an exponential function into an oscillatory function. Now, we could achieve the same effect using even more complex numbers, but ones that are more realistic algebras, like Euclidean algebra, for example. The point is that complex numbers introduce an essential feature of the underlying nature of the reality that many systems in nature come back and return on themselves. So to illustrate how powerful this kind of abstraction can actually be, Luke Kaufman derives a good part of the mathematical structure of physics from an even simpler abstraction in his presentation on non-commutative worlds. Anyway, back to the Mandelbrot set. Notice as we are scaling how many of these fractal structures look natural, cellular, vortex-like because of this quadratic relationship. Now, the main macroscopic features of the Mandelbrot set are a cardioid and a circle. A cardioid is generated when a circle rotates around another circle. So we might expect these shapes to be associated with rotations or with rotational resonances. A cardioid is also the inverse of a parabola across the unit circle. And we will return to this inverse relationship later and what it suggests about the relationship between the real world and the maths. For now, though, let's just mention that the cardioid is also the shape that's traced by the E and the B fields in a circularly polarized photon when it's coming right at you, that is. So, where might we look for an answer to our question? We need to find a simple set of laws that operates at all scale factors of nature and that behaves in a fractal way, and that could account for these spiral or these helical rotational formations. So, could electromagnetism be our prime contender? As far as we can tell, everything in the universe is made up of energy density. Everything that we are familiar with is made up of particles, either in the form of radiation or rest massive particles. Now, the nature of these particles is itself partly electromagnetic, as John Williamson, Martin van der Mark, and Vivian Robinson's work is actually illuminating. So these things exist everywhere that we know of, and they can transform into each other. Is it possible then that electromagnetism can influence structural formations in length scales from the galactic to hurricanes to living things and even down to elementary particles? Let's think about this. Electromagnetism has basic laws that we understand pretty well, but can they yield fractal, spiral, or helical structures that we see in nature? So let's investigate this from first principles. We know that opposite charges attract and like charges repel. With electric current, though, it's the opposite. Currents flowing in the same direction attract each other, and currents flowing in opposite directions repel each other. and what happens when they meet. If the currents are confined in solid-state wires, they'll just approach each other and then remain beside each other because the metal atoms are actually fixed in place. But in plasmas, both the ions and the electrons are free to move, and they do. So, plasma currents will approach each other and then they'll begin to twist around each other. The interference from the magnetic fields serves to stabilize and constrain that central current channel. This is called a Birkeland current filament in honor of Christian Birkeland, the Norwegian plasma physicist who explained the aurora borealis phenomenon. So if we use a simple vector to represent the magnetic field of a right-hand rule current strand, and then we add a second current strand separated by, say, a unit radius, we can get an intuitive sense of the shape that such a rotating system of fields might generate. And if we combine the vectors for the two adjacent strands into one, we get a spiral vector field. Does this imply that parallel electric current flow through any partially ionized fluid medium can result in a spiral or a helix? Now, the Z term in the simulation
referring to the ether
is chosen just to model the aspect of the flux rate, where the current helix is increasingly vertical the closer you get to the center of the channel, which represents the strongest current flow. This also illustrates, by the way, how the same field can be operating both in the axial and the equatorial directions of the same system, depending on how far they are from the axis. Now, since particles have spin, they also have angular momentum. And by the way, notice how all of those equations are quadratic. Photons also have angular momentum. And as charges flow in a plasma current, they're going to flow in a helical path, which means plasma currents will also have angular momentum as they flow. So if we couple two of these currents with angular momentum that are going in the same direction, the collective effect must yield a rotating system for angular momentum to be conserved. And if you consider how many charged particle trajectories that there are in that current system, we should probably expect to see a fractal rotating system within rotating systems. The Nobel Prize winner Hans Alfvén, who was a student of Christian Birkeland, clarified from Maxwell's equations that plasma phenomena scale. They increase, for example, in length in proportion to their increase in duration. So if you scale down a 50 millisecond, 1 kilometer long lightning discharge by a factor of about 50,000 to the size of a 2 centimeter spark discharge in the lab, it will also have a duration about 50,000 times shorter, of about a microsecond. But otherwise, they are structurally very similar. So if we look across all scale factors of the universe, scaling in time and physical dimension, we should expect to see electromagnetic plasma structures. So before we look at research that might serve as evidence of this electromagnetic influence, let's consider what shapes we would expect to see in nature if electromagnetic scalable plasma phenomena were at work. So spark discharges like lightning occur in filaments. Atoms, s orbitals, and charge fields are spherical. Magnetic fields form concentric tori around the equator of a magnetic system. Subatomic orbitals have lobes, and sometimes also a torus around their waist. So if there are inverse square parabolic forces or rotational resonances at work, we should expect to see shapes also related to cardioids, since they are the space-time inverse of parabolic motion, as well as shapes related to spirals and helices. Solar flares show helical structure, as do laser optical vortices or a circularly polarized photon. And as we mentioned before, when you look at the photons E and B fields end on, they each trace a cardioid shape. Relativistically though, from the photon's point of view, they actually trace a two-dimensional cardioid, because according to relativity, the photon experiences its emission and absorption events simultaneously. Now, in terms of filamentary structure, we do see Birkeland currents in plasmas. We see them in solar coronal emissions and in the magnetosphere of Earth and the other planets. Birkeland currents may also be able to explain an interesting phenomenon that we see on Saturn. NASA's Cassini mission garnered some incredible data and footage of Saturn. Here we see an infrared image taken from above the North Pole, which shows concentric axial topography, which is interesting. And above it, we see an image captured by cosmologist Anthony Peratt, who was a student of Alfvén, which shows the cross-section of the Birkeland current in a laboratory plasma focus device. And this remarkable time-lapse footage that NASA and the JPL put together from the Cassini mission shows distinct counter-rotation around Saturn's North Pole, which is something the standard model has great difficulty explaining. Furthermore, counter-rotation has also been observed at the galactic level, for example Messier 77, as this image from the ALMA array shows. The blue regions show that material is moving towards us, and the red regions moving away from us. Now, in his 2015 paper on Birkeland currents, Donald Scott described the mathematics of this force-free field-aligned current system, which he believes provides a mechanism for counter-rotation. You see that in the Birkeland current, concentric cylindrical regions counter-rotate because the magnetic field changes direction as a function of radial distance from the axis. According to the electric universe folks, this explains Saturn's anomalous counter-rotation and may even also account for galactic counter-rotation. So Anthony Peratt also performed a simulation of parallel laboratory plasma currents, and his results bear a striking similarity to galaxy structure. Now here are a few examples of how subatomic and galactic phenomena exhibit remarkable structural similarity. Now, do galaxies and quantum electron orbitals have the same shape because they are somehow related to similar fractal or resonant plasma scaling? We know that plasma effects do maintain their shape at any scale, so that does make them good candidates. On the right, we see the similarity of the classic sphere in a torus shape of the galaxy called Pogue's object, and also the fine ring nebula just underneath it, compared with some of the latest research into the substructure of the electron. This is work by Dr. John G. Williamson, formerly of CERN and the University of Glasgow, and the late Dr. Martin van der Mark of Philips in the Netherlands, which investigates the way in which energy and matter interconvert. So we'll talk more about this in a moment. Now, in the electric model of the universe, star formation may be also related to the plasma Z-pinch or a Bennett-Pinch effect, which is named after the American plasma physicist Willard Harrison Bennett, since current tends to focus plasma into filaments, concentrating matter as we described above. Now, Bennett hypothesized this effect because the solar wind is not a uniform emission, but it's filamentary in nature.
Part 1.
With this Bennett-Pinch effect